Got another question for the AQA buffer solutions topic, so up to number 3 now. If you want to check out the other videos in the playlist, I'll put the link to that at the top of the screen now. Hope you liked the video, hope you found it helpful, and if you haven't already subscribed to the channel, I'd love you to do so. But as always, the link to the questions in the description of the video if you want to try it first. Okay, so make a start. So we're told at the top of the question it's about weak acids, and it starts off with some pH ranges of some indicators. We've got to identify the indicator most suitable for the titration between propanoic acid and sodium hydroxide. So the best way to tackle this is think about the titration curve for this type of titration. So a typical weak acid strong base titration curve looks like this, and basically what we want is an indicator whose range fits or lies in that vertical section. So you can see that bromocresol green is going to be no good because 3.8 to 5.4 is kind of here. Vertical section hasn't started yet. Bromothymol blue, it's kind of just starting to change here, so it's a little bit too soon. So the best bet is going to be thymol blue, 8 to 9.6, definitely in that vertical section. Moving on to part 2, got to give the expression for the acid dissociation constant for propanoic acid. So the best way to explain it is to start with the dissociation equation, which looks like that. And remember, Ka is the equilibrium concentrations of the products multiplied together divided by the reactant. So there's that there, and just make sure we're using square brackets because that denotes equilibrium concentration. Moving on to part 3, got to calculate the pH of this concentration propanoic acid, and we've been given the pKa 4.87. So the first thing I've done is turn that into Ka. So Ka is 10 to the minus pKa, so that's coming out at 1.35 times 10 to the minus 5. Propanoic acid's a weak monobasic acid, so the H plus concentration for a weak monobasic acid is equal to the square root of the Ka multiplied by the original concentration of the acid. So we've got both of those numbers there, so there's the Ka value, there's the original concentration of the acid. So the H plus concentration is coming out at 1.16 times 10 to the minus 3 moles per centimetre cubed. All we need to do now is minus log that for the pH. Remember, we've got to give our answer to 2 decimal places. So pH is coming out at 2.935, which to 2 decimal places, obviously 2.94. Moving on to part 4, so we've got some information about butanoic acid. We've got its Ka value, and we've got volume and concentration information for sodium hydroxide and butanoic acid. So we've got an alkali and a weak acid here, so they're obviously going to react with each other via a neutralization reaction. So we're going to need the equation for that. So there's that there, and now I'm going to use the concentration and volumes to work out the initial moles. So you can see we've got that many moles of the acid, that many moles of the alkali. So now we need to work out what's going to be left over at the end of the reaction. So there's the final moles there. I'll just quickly explain these. So starting with the sodium hydroxide, it's the lowest number of moles, and so therefore it's the limiting reagent, so it's all going to react. The butanoic acid is going to react in a 1-to-1 ratio, so we're going to lose 0.002 moles of that. So if we subtract 0.002 from the starting moles, we get that. And then the other thing we need to bear in mind is how much salt is going to be formed. So remember, that's the limiting reagent. So again, we've got another 1-to-1 ratio. So we're going to get that many moles of salt. I've included the water as well, but that's not going to feature in the calculation. So the important thing to realise at this stage is that we have a weak acid and the salt of the weak acid present in the same beaker at the end of the reaction. So we've got a buffer solution. So to calculate the H plus concentration for a buffer, we multiply the Ka by the acid concentration and divide by the salt concentration. So this is the Kassadova salt expression, I call it. So you can see in this row here we've got the moles of the acid and we've got the moles of the salt. So these aren't concentrations, but everything's in the same volume, they're all in 45 centimeters cubed, so we can just use these mole values. So that's given us an H plus concentration of 3.775 times 10 to the minus 6 moles per decimeter cubed. All we need to do now is minus log that to get the pH, which comes out at 5.42. And finally, part 5, student plans to titrate butanoic acid solution with a solution of ethyl amine. Explain why this titration could not be done using an indicator. So the thing we've got to appreciate here is butanoic acid is a weak acid, we already know that, and ethyl amine is a weak base. So really helpful if we just sketch up the typical weak acid, weak base titration curve. So there's the titration curve there, and you can see the pH change is very, very gradual. There's no vertical section, so an indicator is not going to be any use for that.